Hello, hello, and welcome to this video. This would be the last video on collections container data types. We have covered chain map, counter, deck, default deck till now. In the next video, we will look at the example of all these types. So we will continue with name tuple and we will finish this in today's video. So we start with name tuple. Name tuples assign meaning to each position in a tuple and allow for more readable self-documenting code. They can be used wherever regular tuples are used, and they add the ability to access fields by name instead of position index. So this is the constructor, takes type name and field names. Rename is equal to false, defaults none, and module none. Returns a new tuple subclass named type name. The new subclass is used to create tuple-like objects that have fields accessible by attribute lookup, as well as being indexable and iterable. Instances of the subclass also have a helpful docstring with type name and field names, and a helpful wrap-through method which lifts the tuple contents in a name is equal to value format. The field names are a sequence of strings such as X, Y. Alternatively, field names can be a single string with each field name separated by white space and or commas, for example, X space Y or X comma Y. Any valid Python identifier may be used for field name except for names starting with an underscore. Valid identifier consists of letters, digits, and underscores, but do not start with a digit or underscore and cannot be a keyword such as class, for, return, global, pass, or range. If rename is true, invalid field names are automatically replaced with positional names. For example, ABC, DEF, GHI, ABC is converted to ABC, comma, underscore 1, comma, GHI, comma, underscore 3. Eliminating the known Eliminating the keyword def and the duplicate field name ABC. Defaults can be none or in table of default values, since fields with a default value must come after any fields without a result. The defaults are applied to the rightmost parameters. For example, if the field names are XYZ and the defaults are 1, 2, then X will be a required argument, Y will default to 1, and Z will default to 2. If module is defined, the underscore module underscore attribute of the name tuple is set to that value. Name tuple instances do not have per instance dictionary, so they are lightweight and require no more memory than regular tuples. To support pickling, the name tuple class should be assigned to a variable that matches type name. So we have a point variable and name tuple type name is point, and we have two field names X and Y. And we create a point with value 11 comma y is equal to 22, and p0 plus p1 is 33. If you assign p to x comma y, then xy will become 11 and 12. P dot x plus p dot y will be 33, and p is a point with x is equal to 11 and y is equal to 22. So this is the example. You instantiate with positional or keyword arguments, indexable like plain tuple, unpacked like a regular tuple. Front fields are also accessible by name, and readable left with name is equal to value style. Name tuple are especially useful for assigning field names to result tuples returned by the CSV or SQLite 3 modules. So we have an example, employee record. Name tuple is employee record. And we have name, age, title, department, and pay grade. And we import CSV module for employee in the map of employee record dot underscore make. We read the CSV file, open as read binary. We print employee name and employee title, and then we import SQLite. We connect to company data. We get a cursor, we execute on the cursor, select name, age, title, department, pay grade from employees. And in the map, we make the employee record from the cursor fetch all, and we print the employee name and employee title. So we have not covered CSV or SQLite module. We will cover them soon, so that these examples will make much more sense. In addition to the methods inherited from tuples, name tuples support 3 additional methods and 2 attributes. To prevent conflicts with field names, the methods and the attribute names start with an underscore. One is underscore make, which takes an attribute. Class method that makes a new instance from an existing sequence on it or table. We have already seen the underscore make in action. Then we have underscore as dict. Return a new dict which maps field names to their corresponding values. Then we have underscore replace. Return a new instance of the name tuple replacing specified field with new values. So here x was 11 and it was replaced with x is equal to 33. And for party num comma record in inventory.items, we assign to inventory part num record underscore replace. Price is equal to new prices part number and timestamp is equal to time.now. Name tuples are also supported by generic function copy.replace. Then we have underscore fields, tuple of strings listing the field names, useful for introspection and for creating new name tuple types from existing tuples. So if you look at the fields of P, those are X and Y. And then we create a name tuple called color. There are 3 colors, red, green, and blue. And then we create a pixel name tuple, which takes the point dot fields and color dot fields. So pixel 11, 12, 128, 255, comma 0 will assign 11 and 12 to X and Y. And red, green, blue will give the value of 128, 255, and 0 respectively. Then we have underscore field defaults. So this one has 2 fields, account, name tuple has 2 fields, type and balance, and defaults is 0. So field defaults for balance is 0. And type is constructed with premium. So here type is premium and balance is 0. To retrieve a field whose name is stored in a string, use the get attribute function. We get attribute p of x of p, we get 11. To convert a dictionary to a name tuple, use the double star operator. So we have this dictionary x with 11 and y with value 12. We put it inside the constructor of the point and we received our name tuple. Since a name tuple is a regular Python class, it is easy to add or change functionality with a subclass. Here is how to add a calculated field and a fixed width print format. So from the name tuple point x comma y, we create another class point, and we have slots, which is a private variable, to empty unit. And then we have hypotenuse, which takes a self and computes x square plus y square, and then takes power of half, that is square root of x square plus y square. And then in the string, we print the fixed width print format we use to print x, y, and hypotenuse. So for p in point 3, 4, point 14, 5 by 7, we print p, and we have 2 point objects printed. The subclass shown above sets slot to an empty tuple. This helps keep memory requirements low by preventing the creation of instance dictionaries. Subclassing is not useful for adding new sorted fields. Instead, simply create a new name tuple type from the fields attribute. Point 3D, name tuple point 3D, it takes the fields of point and adds another field z. Docstrings can be customized by making direct assignment to the underscore underscore fields. So here book is a name tuple with 3 fields, ID, title, and authors. And we add to the docstring hardcover book in active collection, 13-digit ISBN to the ID doc, and for the title doc, title of first printing, and authors doc is list of authors sorted by name. So there are some pointers. See typing.name tuple for a way to add types typing for name tuples. It also provides an elegant notation using the class keyword. So we have a component name tuple inherited from name tuple. Part number is integer, weight is float, and the description is optional string initialized with none. C types.simple namespace for a mutable namespace based on an underlying dictionary instead of a tuple. The data classes module provides a decorator and functions for automatically adding generated special methods to user-defined classes. Now we come to ordereddict objects. Ordered dictionaries are just like regular dictionary. Note that we no longer need the use to make of ordered dictionaries because I believe after it has, you'll see this. What I want to say will be clear in this paragraph. Ordered dictionaries are just like regular dictionaries, but have some extra capabilities relating to ordering operations. They have become less important now that the built-in dict class gained the ability to remember insertion order. This new behavior became guaranteed in Python 3.7. So essentially, if you are programming after 3.7, which you should be, because I believe that is end of life, so ordered dict are not very useful anymore. Now, for the lifetime of Python, I will have to figure out that somewhere. Okay, so ordered dicts are not very useful anymore. Some differences from dict still remain. The regular dict was designed to be very good at mapping operations. Tracking insertion or order was secondary. The ordered dict was designed to be good at reordering operations. Space efficiency, iteration speed, and the performance of update operations were secondary. The ordereddict algorithm can handle frequent reordering operations better than dict as shown in the recipes below. This makes it suitable for implementing various kinds of caches. The equality operation for ordered dict checks for matching order. A regular dict can emulate the order sensitivity equality test with P is equal to Q and all K1 is equal to K2 for K1, K2 in JIT P, Q. The pop item method of ordered dict has a different signature. It accepts an optional argument to specify which item is pop. The regular dict can emulate ordered dict's od.pop item last is equal to 2 with d.pop item, which is guaranteed to pop the rightmost item. Excuse me. A regular dict can emulate ordered dict's od.pop item last is equal to false with k colon next with a d, comma d.pop k, which will return and remove the leftmost first item if it exists. Ordereddict has a move to end method to efficiently reposition an element to an endpoint. A regular dict can emulate orderedict's od.move to end k comma last is equal to 2 with dk is equal to d.pop k, which will move the key and its associated value to the rightmost or last position. A regular dict does not have an efficient equivalent for orderedict's od.move to end k comma last is equal to false, which moves the key and associated atom to the leftmost first position. Until Python 3.8, dict lacked the underscore reversed underscore method. So we have ordered dict, several constructors, takes dictionary, mapping, or iterable. Return an instance of a dict subclass that has methods specified for rearranging dictionary order. First is pop item, last is equal to true. The pop item method for ordered dictionary return and removes a key value pair. The pairs are returned in first out order if last is true or first in first order if false. Move to end takes a key and by default last is true. Move an existing key to other end of an ordered dictionary. The item is moved to the right end if last is true, the default, or to the beginning if last is false. Radius key error if the key does not exist. So this is an example of that. In addition to the usual mapping methods, ordered dictionary also support reverse iteration using reverse. Equality tests between ordered dict objects are order sensitive and are roughly equivalent to list od.items is equal to list od2.items. Equality tests between ordered dict objects and other mapping objects are order sensitive like regular dictionaries. This allows ordered dict objects to be substituted anywhere a regular dictionary is used. Now, some examples and recipes are here. It is straightforward to create an ordered dictionary variant that remembers the order the keys were last inserted. If a new entry overwrites an existing entry, the original insertion position is changed and moved to the end. So we have last update ordereddict, inherited from ordereddict. So stores item in the order, the keys were last added. So it has a set item class, takes key value, and it calls the key value set item of this ordereddict super, that is parent method's call, and then it calls move to end to move the key to the end, so that the order is maintained in the reverse order. An ordereddict would also be useful by implementing variants of functool.lru cache. So here we import some collections ordereddict and some time monotonic, and we implement the time bounded LRU. The constructor init takes a function, max size 128 and max size 30. Create the cache from an ordereddict object, assigns function to func, and max size and max age are also assigned. In the call method, if the argument is in the cache, then it is moved to the end. Timestamp and result are taken from the cache args. If monotonic minus timestamp is less than equal to self.maxage, then result is returned. Then result is assigned the return value of the func with the arguments, and then monotonic value and result are assigned to self-cached args. If the length of cache is greater than self.max size, then you pop the last item and return the result. Then similarly, you have multi-hit LRE cache that defers caching the result until it has been requested multiple times. To avoid flushing the LRE cache with one-time request, we don't cache until a request has been made more than once. So here, max size 128, max request is 4098, and cache after 1. So like previous implementation, we create two different ordereddict objects, requests and cache. We have func, max request, max size, and cache after. Those are the object variables. And like the previous function, we have the args. And if request args is the count is more than 1, then you put it inside the cache. Okay. And you pop the item if the request is greater than max requests. And similarly, we pop the item and put the result in the cache, and similar stuff is there. Now we move on to ordereddict objects. The class ordereddict acts as a wrapper around dictionary objects. The need for this class has been partially supplanted by the ability to subclass directly from dict. However, this class can be easier to work with because the underlying dictionary is accessible as an attribute. So there are three constructors like ordereddict class that simulates a dictionary. The instances contents are kept in a regular dictionary, which is accessible via the data attribute of ordereddict instance. If arguments are provided, they are used to initialize data like a regular dictionary. In addition to supporting the methods and operations of mappings, ordereddict instances provide the following attribute: the data, a real dictionary used to store the contents of the ordereddict class. Then we have user list objects. This class acts as a wrapper around list objects. It is a useful base class for your own list-like classes, which can inherit from them and override existing methods or add new ones. In this way, one can add new behaviors to lists. The need for this class has been partially supplanted by the ability to subclass directly from list. However, this class can be easier to work with because the underlying list is accessible as an attribute. So constructor takes a list as an argument. It's a class that simulates a list. The instances contents are kept in the regular list, which is accessible via the data attribute of either list instances. The instances contents are initially set to a copy of list, defaulting to the empty list. List can be any variable, for example, a real Python list or a user list object. In addition, this is the same thing. Subclassing requirements. Subclasses of user list are expected to offer a constructor which can be called with either no arguments or one argument. list operations which return a new sequence attempt to create an instance of the actual implementation class. To do so, it assumes that the constructor can be called with a single parameter, which is a sequence object used as a data source. If a derived class does not wish to comply with this requirement, all of the special methods supported by this class will need to be overridden. Please consult the sources for information about the methods which need to be provided in that case. Then we have user string, which acts as a wrapper around string objects. It's a similar description. Now we can directly subclass from str. So it takes a sequence, that is the constructor, and the real string is in the attribute data. So let's go back to previous page and we'll see what is the next topic which we are going to handle. So next we have where did we go? Yeah, abstract base classes for containers, collection.abc. So we'll see an example of whatever we have covered in the next video, and we will also touch the theory of abstract base classes. Okay. So I hope that you are finding this video, these read-throughs useful for learning the standard library of Python. So I'll take my leave here and we'll meet again after 4 days with another video on standard library. So thanks a lot for watching the video. Have a great day and enjoy.